Alright, so here we are, and first let's look at the schematic diagram for the control card, the CPU card. Well, the first thing I wanted to do was really just figure out how the what these NAND gates are doing, because I know this is some sort of clock logic, or let's say read-write signal logic that's needed. Just by reading around on the internet, I was starting to remember that the 6502 had a particular requirement for the read-write signals, and I can't remember a thing obviously about how these work. So the first thing I wanted to do was trying to figure out what these did. So armed with a 74LS00 datasheet, you can look at the pins and slowly just look at the tracks and go, okay, you know, pin 1, pin 2 are connected together, and so forth. You know, pins 3, 4 and 5 are all shorted together, and pin 6 is going to the other chip. So just by looking at these pins, this is pin 1 through to 7, 8 through to 14, you can basically see where the tracks are going and form a schematic diagram just by looking at the PCB. It's not too difficult once you've got the data sheet to hand, and you've got to sort of like flip it over mirror image, and then you can see which pins connect to where. So that's basically what I've been doing, and I started with those NAND gates. Now, and you notice it's best just to do things on a bit of paper with a pencil, because you can scratch it out, you can see I've made mistakes, I've had to rethink things, but eventually you start to see where these pins go, so where they connect. And as I said before, pins 1 and 2 are connected together on this NAND gate, which turns this NAND gate into an inverter, and then it goes to another NAND gate. If you remember, it was pins 3, 4 and 5, which is this connection here, 3, 4 and 5, which goes to another NAND gate with its input shorted, which forms another inverter. So really these are just like two inverters. Okay, that's the logic for that. And that's coming from these capacitors here, which happen to know is part of the clock circuit. So okay, we don't know how this connects to the CPU really, except that we've got these two pins. We've got Thigh 0, which is an input, and you've got Thigh 2, which is an output. And again, just by looking at the 6502 datasheet, you can see which pin does what. So by putting these capacitors across, one of them's a variable capacitor, a trimmer for fine adjustment, and the other one's just a fixed 47 PF capacitor. By putting those capacitors across the Phi 0 and Phi 2 allows the CPU to clock, to actually oscillate. So that's like an internal oscillator. Okay, what we're doing this for is to give buffering, so we're not really affecting the oscillator of the CPU, and we're taking the signal straight from the output for our own purposes without loading the capacitors or loading the oscillator frequency at all. But it's in phase, the output is the same as the input. Right, then you start to look at the other chip and you think, okay, now what's going on? And again, using the datasheet for the 74LS00, you can see that it connects to these two NAND gates here, and there's also a third NAND gate further down here, and there's also another one at the very bottom. These 4 NAND gates here, and you'll notice I've had to, you know, this is how it goes. You figure something out and you think, oh, that's not right, so you stop and you start again. So that's why I like pencils and rubbers and things. It's just very easy to quickly get an idea of what's going. It doesn't really matter if it's messy at this point. And then you start to figure out what connects to what. Here's a rewrite signal from the CPU, from the 6502. It also connects to 2 of these gates. It connects to this gate here, which is gate 4, and this gate here, which is gate 1. Alright. This input here is also tied to plus 5 volts, which basically means turn that into an inverter. The other way to do this would have just been to take the 2 inputs and tie them together. You'd get this exactly the same result. But for whatever reason, back in 1987, I did it the other way and I tied it to plus 5. But it's the same thing. So that's really just really an inverter. It's very common to use NAND gates as inverters. They're very useful gates actually. You've got a read-write signal here coming in. Eventually again, just tracing it through, looking at the PCB, looking at the data sheet. These are the two 74LS00 here. You begin to realise that this one's connected to the ROM, so that's a read signal. Okay, we're getting a read signal here, which connects to the ROM, so we can read data from the chip. And this one connects to RAM, so we can write data, and that connects to this chip here, the 6116 RAM. So these are giving us our read-write signals. That one's read, that one's write, to the chips, to the read EEPROM and to the write RAM. So you start to figure out, and these connects to the output enable, which turns the chip on. So you start to figure out what the read-write signals are. Then you've got another little bit of logic down here, which is it's got a diode here and another NAND gate, which is acting like an inverter. And the output of this goes to one of the output ports. Goes to this 74LS77, okay, which drives the pins here. So again, this is what we're doing. We're just going backwards and forwards. We're looking at the PCB. We're looking at the data sheet for the chip, and we're converting that to the best of our knowledge, trying to keep it neat, but it never is. And you figure out what pins connect to where, just reverse the whole thing, and you end up with a schematic diagram like this. This actually forms a gate. I think it's a NOR gate. You've got a diode there, and you've got a diode there, and you've got an inverter there. So, and there's a pull down resistor of 2.2k here. So this is forming really a NOR gate used to drive the port. It's actually a write signal to drive the port. And the reason for that is because read-write signals are not the same signals that you use for the RAM-ROM than what you use for the port. You've also got a signal coming in here, which is from a 74LS138, which is this chip right here, and that's the page decoder. That's so that's taking it's looking at the address coming from the 6502 and selecting whether it's going to be, whether we want to work with the ROM, the RAM, or the port. So there's really three things being addressed as ROM, RAM, and port. And that's what this 74LS138 is doing. It's the decoder which selects the chips that you want to work with, or the 6502 wants to address. So straight away, just by looking at a few tracks, this took about, I don't know, 20 minutes, 30 minutes, something like that. Just basically flipping the board over, you know, looking at the actual pins themselves, tracing it through, say, okay, this pin connects down to here, it goes into this chip here, and so on. You know, you can actually, you know, that connects through here to these pins here. So eventually you build up a bigger picture. You realize, okay, this is the clock. This is giving us our 1 megahertz clock for the 6502 CPU. It's buffered, and then we've got some read-write logic, which is required by the 6502 to actually activate the RAM or activate the ROM, give us read-write signals. And then you've got which is actually connected with the read-write coming from the processor itself. So this is all read-write logic. And then you've got this bit at the bottom here, using another NAND gate, which is inside of here, another NAND gate inside there. Remember, there's 4 per package. So that's another one. And this forms a logic NOR, which works with the decoder, with the RAM, so because it actually comes through here as well from the read-write signal, and that drives the ports. So straight away, well, within half an hour or so, let's say, we've roughly figured out, you know, using data sheets, looking at the PCB, what connects to what, and we've ended up with a rough diagram of the switching logic, the logic for the read-write signal, for the RAM, the ROM, and for the port, which is different. So that's a great start, okay, and we'll keep that for later. Then we've got some other bits and bobs. I'm not going to go through this entirely, but by tracing through the pins from the port and tracing it back to the 2 chips here, which forms the port itself, there's a 74LS77 and there's a 74LS125. So this is output pins. That's an output, it's actually a quad latch. And this is input pins, which is a quad tri-state buffer. So output pins, input pins, again armed with the data sheets, which are all freely downloadable off the internet. You can look at those chips, look at the pins, see what the pins do, and we've been able to determine just by looking at how the port is addressed. That's interesting, because this will tie in with the software. You can look at the actual pins, and from the legend that I've wrote on the board with my little permanent marker pen all those years ago, you can figure out how the software is going to work, because you can look at, okay, we've got two chips here. One is working on D0 and D1, which is the data line 0 and data line 1. They're connected to the data bus of the 6502 directly to D0 and D1. These are the read, or if you like, input signals coming into this chip here. The other chip is at the same address, but it's basically, you've got three. You've got D2, D3 and D4. That's data line 2, data line 3, data line 4, also connected directly to the 6502 data bus. And you can, because we know what the writing is, you can barely make it out, but it's there. We know that D2 is the CW ident that keys the oscillator on and off on the analog board. We know that D3 is a mute signal, and what that does is it reduces or switches off the audio through link from the receiver to the transmitter. So if somebody's talking and through the system, and if it's active, if this mute becomes active, it cuts them off. You can still send CW, it's just that you won't hear the person speaking. And that's used in situations where there's a timeout situation. They've been talking too long, they haven't let go of the microphone, and it's probably over 2 minutes, and the repeater will time out. And it does that, it puts the mute on, which cuts the person off right in their tracks. You can't hear them anymore, but the CW can then take over. So that's what the mute does, and that's on D3, data bus 3. Then you've got the PTT TX line. This puts the transmitter into transmit, and that's on D4. These other pins are not connected. D5, D6 and D7 on the data bus to the port area we're talking about, they are not connected. So we actually have some spare ability here. We could actually connect more inputs, 3 pins that wouldn't do anything we like with inputs or outputs. But at the moment, with this design, they're not used. So we've got 2 input pins and we've got 3 output pins. And those pins we've figured out are at the same address because they come from the same page decoder. It's the same pin from the decoder, so we know this is at the same address. And we've figured out that because we know what the pins do, because of the little bit of permanent marker that's left, we kind of know what the pins do. We can basically figure out, okay, that's squelch detect, that's the tone detect, this is the CW, that's the mute, and that's the PTT, which puts the transmitter into transmit. So this is actually very handy, and we've done that purely from the by reverse engineering the schematic using data sheets, because we now know what we're testing for, which will tell us what the block of code that we're looking at, what it's doing, because we're going to be testing these bits. We're going to be doing a logical AND, like AND 1, AND 2. We're going to be ANDing for those bits, which will tell us what the code does. For instance, if it was ANDing, if we were doing a logical AND with D0, we would know that's like a 1, okay, because it's the first one, that'll be 1. Then we know that that chunk of code will be doing the squelch detect activity, and the next one, if we're ANDing for 2, bit 2 if you like, we would be checking for the tone burst, and so on. So that's been very useful, just to look at the data sheets and determine what the pins are actually doing. Very useful later on. This is the 74LS 138 decoder, and basically what we're saying here is, that's the chip here, of course, that's the 138. What we're doing here is we're looking at A13, A14 and A15. They're address lines from the 6502, and we're saying, okay, they connect to A0, A1 and A2 of the decoder. So there's only 3 lines that we're interested in for the decoder. And if you work out what these lines can address, you realise that this decoder is working in 8K pages. So each output, which is, these are all the outputs, which is Y0, Y1, Y2. Because these are addressed as 8K blocks in memory, imagine an 8K block of pages, that gives you a full address of 64 kilobytes of complete memory space, which is the maximum capability of the 6502 is 64K. The chip itself is in a constant working state. Everything's enabled. These two pins go to ground. This pin goes to positive. And again, we've figured that out just by looking at the datasheet for the 138 and looking at the tracks and seeing where they go. One of them will go to ground, one of them will go to positive. You can just trace it through. That tells you that the chip's on permanently. Oh, there's Y7 there, of course. So it is Y0 to Y7. Page 0, which is the bottom 8K page, is used for the RAM. And we can see that because it's connected to Y0. And we know that this address range is 8K pages. So Y0 connects to the RAM, okay, which is page 0, which is correct because the 6502 requires RAM at the very bottom page, at page 0, for the stack. The way that the RAM works, it has to have RAM in that bottom page, and there it is. It's Y0, and it connects to the chip select pin of the RAM. So that's all correct. The next page is to the port. So this is Y1, if you like, everything above. It's basically page from 8K to 16K, that one. This connects to the port. There it is there. These two chips connect together, they're on the same address, if you like, in the same block. Yeah, so we have loads of unused outputs here. We could have had plenty of other peripherals on the card if we wanted to, all addressed from these block outputs from the decoder. The very last one is Y7, and Y7, as we trace it through, goes to the ROM, which is the ROM there, the 2716 EEPROM. And that means, because it's Y7, it's at the very top of the memory space. It's right up towards the last 8K block of the 64K address space. So that means that the ROM is at the very top of the memory address space, the RAM is at the very bottom of the address space, and the port is on page 1, like page 0, page 1, and then page 7 at the very top. And remember, these are all 8K pages, so that's kind of how the whole thing is decoding. And we've determined that purely by tracing from the datasheet of the 74LS138 and seeing which chip it goes to the chip select of that, the chip select of that, or the enable pins of the port. What other notes have we got? I'm just going through my notes here. So I was just working out the size of the address range here, thinking to myself about which lines, like there's A13, A14, A15, looking at the size of the pages that you know, to work out the range of the blocks and everything. I was just trying to get that clear in my head. And then further down here, I was looking at the logic NOR, which is this, where you've got the you've got two diodes and an inverter with a pull down resistor, and I was really just sort of seeing what on earth that was all about. And it works out that you've got a signal from the decoder, which is the output pin from the decoder, and you've also got a write signal. You'll notice that's a bar, so that's like a negative going pulse. That's also a bar, so that's a negative going pulse. These two waveforms, if you like, or signals, then go through the NOR, and that gives you a write output signal which goes to the port. So really I was just sort of working out how the port was being accessed, how is the write signal working when you come to write to the output chip, and this was just a logical process of, well, how does it work? And okay, looking at the input pins, this is the 74125 here, looking at the input pins, managed to trace through that two of the control signals were joined together, and because the two control signals of these are bilateral switches, so when the control is in a position in a particular logic state, the signal can either pass through. When it's in the other state, it blocks the signal from passing through. And these are tri-states, so these go high impedance when they're not in use, so it doesn't affect anything else on the data bus. These connect to data bus 0 and data bus 1, which is what we were looking at earlier on. And these are the actual port pins here for the tone and for the squelch input signals. But because these are actually joined together, you know they're working in tandem. You only have one signal coming in and it's operating both at the same time. That was good to know. Looking at the timing of the address, the chip enable, the output enable when the data bus is in a valid state. So I was just looking at the timing of the waveforms and how that works with the NOR logic. Now that's kind of it, you know, and it's really just a process of looking at the PCB, as I said, looking at the data sheet, seeing where the actual connections go, and going, okay, that pin there connects to that pin there, that pin there connects to that pin there, and so on, and just making a note roughly of how the circuit works roughly on pencil and paper. This is how I do it. I believe that's, you know, that's how other people do it too. You end up with like a bunch of paper, and that bit there is me trying to figure out the 566, which is the triangle oscillator for the CW. That's the CW oscillator, and it goes through a little CR network here, which pretty much gives you a pretty decent sine wave output, and that goes to the transmitter when it's sending CW ident, and so on. So you can see it's just handwritten notes, and it doesn't have to be particularly neat, because in the next video we're going to be looking at taking all of our rough notes, now that we've got a decent idea how everything's connected, and we're going to put it into a proper schematic diagram using KiCad or KiCad. You can pronounce it both ways, KiCad, KiCad. That will allow us to generate a schematic diagram from our notes, which will look much neater, and so on. So that'll be coming up very soon, and I hope you've enjoyed a little insight into reverse engineering armed only with a PCB. Okay, so thanks for watching.